First of all, I'd like to thank organizers for giving me opportunity to present my research today. So this work is joint work with my students, Soma Shiraki and Professor El Barkai. This photo shows some of my collaborators at the library Izakaya in Tokyo during the previous Studies conference. And he is Günther Radons, but he was also involved in this project in the early stage, but sadly he passed away last year. I will discuss my research on the subrecoil-laser-cooled atom and its implication for the quantum technology such as quantum computing and precision measurement. So Doppler cooling is a fundamental cooling technique where the atom lost energy by scattering the photon from the counter-propagating the laser beam. And roughly speaking, the atom experiences friction-like force like this due to the Doppler effect. This which enabled the drift towards the zero velocity. However, the laser beam goes in random directions due to this random radiation, so there's a fundamental temperature limit, so-called recoil limit. To overcome this recoil limit, more advanced techniques are required. Subrecoil laser cooling is overcome this recoil limit. It is impossible to cool atom below subrecoil limit without relying on friction. So instead, inhomogeneous diffusion on momentum space are used. When atom moves slowly enough, then the interaction between the laser may stop due to the quantum influence. This phenomenon is known as velocity selective coherent population trapping. So this is like an interaction between the laser. So when the velocity near to the zero, so the interaction stops with the laser. Surprisingly, this kind of selective, velocity selective mechanism can cool atom below the recoil limit. So because the propagator of the momentum cannot reach to the steady state, but non-stationary regime, so which means goes to zero momentum. So we model this process by a stochastic framework. In our model, in our stochastic model, so we assume the atom's momentum undergoes random walk, but this random walk is not usual random walk, it's state-dependent random walk, so on the momentum space. So the feature of this random walk is jump rate depends on the momentum. So this is RP is a jump rate. So this in the function of the RP is proportional to the absolute value of the momentum to the power alpha. So this power alpha is a very important parameter. So this parameter can choose by using the velocity selective population trapping. So this model is a random walker can change the momentum according to this jump rate. So we refer to the time between the momentum jumps to the flight time because random walkers goes constant speed between the jump. So this flight time distribution follows the exponential distribution like this. But this exponential distribution depends on the current momentum. So the whose mean value is described by this RP. So 1 over RP is a mean flight time. So this flight time depends on the current momentum. So the previous velocity selective mechanism can mimic. So in our random walk model, so jump is according to the Gaussian PDF, like this. So over the time, the momentum will eventually become near zero momentum, which is called the trapping region. So this momentum in this region, due to the quantum interference, so this state changed very long time. So it's trapped in this state. So to analytically trackable, so we use following approximation. So it's called uniform application. So jumps, momentum change is according to the random walk, but we assume this momentum change identically independent and identically this random variable. So, and whose distribution is follows a uniform distribution, like this. So this is the time series of the momentum. So this momentum is, if the momentum change, the momentum change to the according to the uniform distribution. So this model is called rate-induced Levy walk. So these figures are the time series of the momentum and displacement position of the atom for the two stochastic models. Left-hand side is inhomogeneous random walk model. So, and right-hand side is uniform approximation, so rate-induced Levy walk. So momentum eventually goes to near zero without friction. And this two models shows similar behavior, but the dynamics, detailed dynamics are different. Although this is different, but the statistical behavior of the momentum and also the displacement are quite a nice agreement, as I will show. So we briefly explain the infinite invariant density that emerges in subrecoil laser cooling. This is a master equation of the evolution of the momentum distribution. So this is loss term and the gain term, and described by this jump rate. So to obtain the formal steady state, so we set the equal 0 on the left-hand side. Then we obtain the formal steady state solution for the momentum distribution. And this is described by the tau p. This is inverse of the rp. And this rp is power or behavior. So this formal steady state is proportional to the p to the power minus alpha. So when the alpha is greater than 1, this distribution cannot be normalized due to the divergence of the zero momentum. So this type of the non-normalized non-normalized density called the infinite invariant density. So in the subrecoil laser cooling, so this kind of the infinite invariant density plays a critical role in the cooling process. So let me summarize the previous studies. So in theoretical model of subrecoil laser cooling, infinite invariant density naturally emerges in the atomic momentum distribution. This model exhibits non-ergodic behavior and the long-time statics of time average observable, which are governed by the infinite ergodic theory. So furthermore, it has been shown that there exists an optimal tuning of the system parameter that maximizes cooling efficiency and minimizing the atomic kinetic energy in the long-time limit. So in these talks, we shift to a focus on the diffusion of the cooling atom. So why this is important? So diffusion in the cooled atom is important in the quantum technologies like atomic quantum technologies, like quantum computing and precision measurement. However, the behavior of the atom at low velocity remains not fully understood. Furthermore, the fundamental question remains, what is the nature of this diffusion? Normal diffusion or subdiffusion or superdiffusion? So we calculate the diffusion property of this model. So this is velocity, trajectory of the velocity and position. So this dynamics can be characterized as flight time distribution and also the flight jump distribution. Both distributions follows the power law. And using these distributions, so we describe the displacement distribution by the coupled Monroe-Weiss, so-called Monroe-Weiss equations. And where this psi is a joint probability of the jump length and the flight time. By calculating the second moment of the displacement, so we obtain this scaling anomalous diffusion. So this power exponent is depend on the alpha, and also there's some transition between the 3/2. So this is a summary of the power exponent. So we see the normal diffusion for the alpha is less than 1, but in between the 1 and the 2, we observe the subdiffusion. And also notably, alpha equal 1.5, there's a minimized exponent. And beyond the alpha equal 2, the exponent transition to the superdiffusion. Furthermore, so we can calculate the force moment and to quantify the non-Gaussianity, we define the non-Gaussian parameter. And we obtain the result for the non-Gaussian parameter as a function of this parameter alpha. So we also find 3 regime. One is a Gaussian regime and a leptochaotic regime and pragmatic regime. So this leptochaotic regime, so we also find maximum of the non-Gaussian parameter. This is corresponds to 1 to 1.5. So this, which means the propagator, shape of the propagator is peaked, highly peaked propagator, which means optimal confinement for the atom. So let me summarize my talk. So we discover the transition of the enormous diffusion in subrecoil-laser-cooled system. So especially, so this point, this parameter, the slowest diffusion in this model. And also this point corresponds to the narrowest propagator here. So this transition point is optimum parameter for the application for the confinement of the atom. So we suggest that this tuning of the system for the very good application has a potential application for the quantum technologies such as compact computing and optical lattice clock, because of the trapping atom is crucial for this quantum technology. So thank you for your attention.